Let's go through activity 5. So let's add these solutions to our second activity with simple linear regression. So when you open up RStudio, as always, you'll want to run library reg class to load in the data and the commands. And for this activity and for homework number 5, you need to update the function find.transformations, because the one in reg class right now has a bug where it doesn't show you the right plots. So if you go ahead and highlight lines 13 all the way down to 72, including the curly bracket, and click Run, that will make that function be updated so that we can use it. All right, so the data set we're going to use this week is the Bulldozer data set, where we try to predict the selling price at auction of a bulldozer based on the usage of that machine. So I'm going to load this up by saying data bulldozer. Doesn't matter if you have quotes or not, it'll load it up the same. And here we go. Let's start out by visualizing the relationship. So let's make a scatter plot showing the relationship between the two quantities here. And in this case, since I'm trying to predict the sale price, that will be my y variable. So I'll start it out with that. And then twiddle my x variable, usage. And I got to say, all right, what data frame is that located in? And in this case, there are a lot of points. So if I make my scatter plot like this, it's kind of hard to see what's going on. That's why I say let's add in these two additional arguments, PCH equals 20 and CEX equals 0.3. That's going to make those points a bit smaller so that you can see the stream of points a bit better. All right, so it doesn't look like there's too much to see here going on in this stream of points. So let's go ahead and fit that linear regression model. I'm just going to copy and paste the commands in here, the stuff in here. Same syntax, oops. Let's copy it, let's paste it. So we got our regression model, and let's go ahead and add that model to the scatter plot. So here's our regression line. So it's kind of hard to see what's going on with the scatter plot itself. There's not much structure in that stream of points, but it looks like the regression line indicates there's a negative relationship. Basically, bulldozers with larger values of usage tend to sell for less than bulldozers with lower values of usage. That kind of makes sense intuitively. All right, so before looking at the slope, its standard error, or making any sort of predictions or confidence intervals, we need to make sure that the assumptions behind that model seem to hold up. The model needs to be a reasonable reflection of reality for us to trust any of the numbers that come out of the regression model. So the way that we do this is by running the command check regression and looking at the errors of the model. We see here's our regression line. The points are scattered away from that line. What do those errors look like? That's where our assumption comes into play. So the first thing we do is we look at the statistical tests of the assumptions. What these are doing is checking to see if you can tell the difference between the data that you've collected, kind of the reality of what's going on, and the model that you're imposing. Now, we know our model is wrong, so it's not a perfect reflection of reality. If we pass the statistical tests, then basically we can't tell the difference, and that's great news. So if we get a p-value of 5% or larger for the assumptions, we pass those tests, and that's what we'd like to see. Most of the time, we're going to end up getting p-values less than 5%, and indeed, here we failed the test for linearity, we failed the test for equal spread, and we failed the test for normality. So what the statistical tests are telling us is that our model is wrong. But we already knew that. We just need it to be an accurate enough reflection of reality to use. And so what I need to do, since I did fail these, is to check the residuals plots to see if those violations of the assumptions are small and can be ignored, or if they're severe enough that I need to abandon the model. All right, so which of the tests failed, which ones passed? They all failed since the p-values are less than 5%. All right, so our model's wrong, but we already knew that. It's basically saying we need to double check to make sure it's kind of an accurate enough reflection about reality. So let's check out the linearity assumption first. And so I'm going to hone in on the residuals plot, the size of the error of the regression model versus the predicted value of the regression model. So what I want to look for here is the presence of any additional structure in the residuals plot. Do I see, when I go from left to right, any sort of curvature, any sort of weird pattern, anything that has a hint of nonlinearity at all? And I look at this and I say, no, I don't see anything. There's not very many points out here to see kind of what's going on out there, but in the places where I do have a lot of points, there doesn't look like there's any sort of curvature. It's kind of a flat rectangular band here. So I would say that the linearity assumption holds up good enough. The relationship looks linear enough. No curvature in the residual plot. What about the equal vertical spread? Are the individual points about the same distance away from the regression line everywhere we look? Well, to check that, we look from left to right and see if the typical size of the residual is about the same everywhere. Once again, it's hard to tell what's going on over here, so I'll just focus in on where I do see points. And I see that, yeah, we have a fairly large amount of error here, either positive or negative, above or below the inferred regression line. But the typical size is about the same everywhere we look. It's not like all of the errors are super, super tiny in this location and then really big in other places. It's always about the same size as we scan from left to right. So I'm going to say it has equal enough vertical spread, typical size of the residual is about the same everywhere. All right, so I'm okay with that. What about normality? Well, what we're trying to do is compare the shape of the distribution of the residuals to a normal curve. So here's a histogram of the residuals, and it looks reasonably well described by a normal curve. But to really make that assessment, we check out the QQ plot. The QQ plot shows the observed values of the residuals vertically versus the values we expected them to have, what they should have had, if the values were coming from a normal distribution. So if those points fall more or less on that diagonal red line, that means we're getting perfect concordance with the observed values of the residuals and what they should have been if they were coming from a normal distribution. And that's pretty much what we do see here. For the vast majority of the points, they're right along that diagonal line, definitely within the upper and lower red dotted bands. We see a little bit of curvature away from the line at the right and at the left side of the graph, but that's actually to be expected. This amount of curvature is nothing to be scared about. This is always essentially going to happen. So I'm going to say that this looks normal enough. So the points are inside the upper and lower red dotted bands, and there's some curve away from the line left and right edges, but this is to be expected. The small amount of curvature isn't anything to worry about. It's only if it was extremely pronounced, like it went, say, from here, like room, like that. A lot of points curving really far away. So it looks like, yeah, none of the violations that the tests are picking up on are severe enough to really be worried. So it seems like our model is a good enough reflection of reality to use. So, all right, with that being the case, why don't we go ahead and visualize our regression model? So visualize model is what we can use to look at the scatter plot, the regression line, and then also confidence and prediction intervals. This legend is in a very inconvenient spot, so I'm going to change its location by adding top right as requested in the problem so that I can actually see what's going on here. So, all right, what we see is that the red line is the regression line, basically describing how the average sale price changes with the usage of the bulldozer. The upper and lower black solid lines represent 95% confidence intervals for the average sale price. So among all bulldozers that have 30,000 hours of usage, we're 95% confident that the average selling price of those is somewhere in between this upper and lower solid black line. Now, typically in business analytics, we're more interested in making predictions for individuals, so my 95% prediction interval, the dashed bands here, give me a range of values where individual prices have a 95% chance of falling into. So if I know that the next bulldozer coming up at auction has 10,000 hours on it, I could say that there's a 95% chance that its selling price will be somewhere between this value and this value up here. I'll have to use the predict command to actually get numbers out. But I can see actually that the prediction interval is extremely wide. I don't really narrow down an individual's selling price with my model all that well. I might have nailed down the average pretty decently. There's not a huge range in values in the confidence interval. But there's so much scattered in this stream of points, the individual selling prices seem to deviate just a lot from each other, that I just can't really nail down the individual prices all that great. Okay, one last thing I say here, that when the assumptions of the regression model are doing their job, it seems to be a good reflection of reality, then by design, if I look to see how many points are inside the 95% prediction intervals, I should expect to see about 95% of the points on the inside and 5% of the points on the outside. And actually, I don't see that here. I see that there's really only very, very few points outside the prediction intervals. And so what that's telling me in this case is that I'm overestimating really the amount of uncertainty I have in this problem. By design, 5% of those points should be outside the prediction interval. I see substantially less than that, so it looks like the numbers that the model's using to quantify the uncertainty are a little bit too big. I'm actually a little bit more certain about predictions than the model is suggesting. But that's more or less a side note here. So we see substantially fewer than 5% of the points outside the 95% prediction interval. So it's not quite the case. Our model thinks there's more uncertainty regarding predictions than what there really is. All right, so let's go ahead and actually make predictions for the sale price, and we're going to make predictions at usages of 0, 10,000, and 30,000. So to do this, we have to create a new data frame, and my convention is to call it 2.predict. And the way that we create this data frame is by making a single column with a name that matches up to the name of the predictor variable used in the regression. So to make the data frame, I invoke the command data frame, and inside the parentheses, I need to give the column a name, and in this case I'm using usage to predict sale price, so I need to say usage equals, and then I need to specify all the values that I want to make predictions at. And so since I have 3 values, I'm going to treat these 3 as a vector, so I'm going to do C and then parentheses, and then list out those 3 numbers separated by commas. And so now I have a new data frame called toPredict. One column, it's named usage, matches up with the X variable used in the model, and 3 values in here. So, all right, we want 95% confidence intervals for the average sale price among bulldozers that have these 3 usages. So how do we do this? Well, we use the command predict. We say what model we're using to make predictions, which is M, and we say that the data frame that contains the values of X that I'm making my predictions at, new data equals, I'm going to give that the name that I made here, 2.predict. And then I need to add the argument interval equals confidence to specify what I'm really trying to predict. I'm trying to predict the average sale price, so I want the corresponding confidence interval. All right, so that first row corresponds to that first value of usage. So I would predict that a brand new bulldozer would sell for just about $80,000. And all right, how much uncertainty do I have regarding the average sale price of all new bulldozers? Well, I'm 95% confident that the average selling price of new bulldozers is somewhere between about $7,500 to $8,300. This row corresponds to 10,000 hours usage. This row corresponds to $30,000 usage. And one thing that we notice is that based on this plot and also what we see here is that the farther we're trying to predict away from the average value of usage in the data set, the farther away we're predicting from the average value of X, actually the more uncertainty we have regarding our prediction. And so we can see that this interval right here at 30,000, well, there's about $18,000 inside this range, whereas very close to the average at 10,000, we see that there's only $4,000, $4,500 inside this range. So more certainty when we predict close to the average here. Okay, so that's predictions about the average sale price over all bulldozers with a certain usage. What about for a particular bulldozer that's maybe just about to come up for auction? So we have a new bulldozer just coming up. What would we predict for its sale price? Well, we use the same syntax, except for we change confidence to prediction interval, because we're going to predict an individual's value. So this first number still gives us the best guess, the point estimate. So if a new bulldozer is just about to come up for auction, I still predict it's going to sell for about $80,000. And these numbers tell you the 95% prediction interval. Basically, I could say there's a 95% chance that its selling price is going to be between $12,800 and $146,000. That's a huge range of values, disappointingly large actually. I haven't really nailed down what the individual bulldozer selling price might be, but that's just the nature of the problem. There's just a large variability in sale prices at each particular value of usage. So not the most useful interval, but hey, it's better than nothing, I suppose. Okay, so I have a few additional observations that you can read over. One additional comment that I wanted to point out is that we do get nonsensical predictions or prediction intervals for this particular value at $30,000 hours usage. And that's just reflecting the fact that, hey, our model is wrong. It looks like a reasonable reflection of reality, but for some predictions or for some applications, that model's just not going to be appropriate. We're going to reach the limits of the model, and in this case, predicting negative values is nonsensical, and so we've essentially stretched the model to the limits. We can't really use it to make predictions out here. All right, so now what we want to do is we want to move on and look at the relationship between sale price and year made. So let's go ahead and make that scatter plot. Let's try to predict the sale price, y variable, from year made. And it's still in that Bulldozer data frame. And if I do this, well, I kind of pick up on some sort of curvature that's going on. It looks like the selling price is relatively flat before 1980, and then there's kind of an arc upwards. So it doesn't really look like I have a linear relationship here. Let's go ahead and fit that model and run check regression to kind of confirm or discount that assertion. So once again, I'm going to copy and paste this right here. And I'm going to add the line corresponding to that model. And so I see, yeah, I have some issues here. So especially in the middle part of the plot, almost all of the residuals are negative here. They're below that regression line, and that's really not what I want to see. So let's run check regression to see the tests and the p-values. We fail the linearity test. We actually pass the equal spread test, and we fail normality. And so looking at the residuals plot, to me, there looks like a very apparent U-shaped pattern here, some distinct nonlinearity. So, all right, when we run into a nonlinear relationship, when we run into a relationship with heteroscedasticity, it may be the case that we need to approach the problem differently. Instead of modeling the observed values of the two variables, why don't we try modeling some transformations of them? So the command find.transformations is going to take our very poor fitting regression model and see what might do better. So what it goes through is it tries raising the original values to powers from -3 up to 3, including the logarithms, and we check to see, okay, do we do any better thinking about it a different way in terms of different predictor and response variables. So here's our scatter plot with no transformation. Here's the scatter plot if we use the suggested transformation, the one that resulted in the highest r squared. And actually, we don't really see too much of a difference here. In fact, we started out with an r squared of 54%, and we increased that to 55% using transformations, but a difference of 1% isn't very impressive. But this is essentially the best that we can do. I want to see, okay, does this model, is this appropriate for modeling the relationship using these transformations? And so this is where the bug was. If you didn't update your find transformations code, the 3 plots here aren't displayed correctly. So this actually is the transformation that gave the highest r squared, second, and third. If you didn't fix your find.transformations, it would be a different 3 plots. So, all right, let's go ahead and try to fit this model. So what I need to do is manually define my transform variables. Xtrans is going to be my transformation of the x variable. And in this case, my x variable is year made, so I need to extract the year made column out of the Bulldozer data frame, and then raise that to the power suggested. So raise that up to 1.75 power. And we'll do that with the y variable as well, use its suggested transformation. So extract that column, which was the sale price, and raise that up now to the 0.5 power, which is just the square root. And now we need to fit that model. I'm going to name it something differently, m.trans, to reflect the fact that you're using transform variables. Y-trans, twiddle, x-trans. I don't need to have a data argument in this case because I defined my x and y variables outside of a data frame. And then we're going to run check regression to see if we do any better using this the transform variables. All right, so we still fail actually every single one of these tests now. So are these violations severe enough for me to want to abandon the model? Well, here are my plots. Kind Kind of hard to tell what's going on here, but maybe I still do see kind of a concentration of residuals kind of going downwards. There might be a little bit of leftover nonlinearity. But there's a lot of scatter. It's hard for me to tell exactly, okay, did I solve my nonlinearity problem or not? Tough to tell. I'm okay with the vertical spread here. It looks like the typical size of the residual as I go from left to right. They're kind of about the same size everywhere. What I am concerned about is normality here. All right, so why I'm not comfortable with the normality is that although I do see a lot of the points inside the upper and lower red dotted bands, I see this little blip that actually goes just outside, and then I see this huge part that kind of dips underneath before coming back in. And this isn't something that you want to be seeing. You want to see, essentially all those points in the middle be inside the upper lower red dotted bands with maybe a little bit of a curvature outside. So this violation of normality is still pretty severe. I wouldn't be comfortable using this regression model. So I'm going to say that no, we can't model this with the transformed variables. The violation of normality is severe. So sometimes, despite our best efforts, we fail. We cannot come up with a model based on what we've learned so far to actually capture the relationship between the sale price and year made. Regression was not appropriate with the original variables, and it still wasn't appropriate after we found the best fitting transformation. So we'll have to stay tuned for how we actually handle problems like these in the future. But that should be it for the activity. Let's make sure it knits just fine, and it may take a little while to knit because these commands take a while to actually run, and it looks like it's pretty good here. So all right, those are solutions. Notice that it lists all those transformations. So if you're knitting to an HTML, you're pretty much stuck with that. If you're in Word, you could feel free to kind of edit out a whole bunch of these. But these are basically all the models with an R-squared of at most 0.2 away below this. So we see there's actually a huge range of acceptable, possible transformations here. My guess is probably none of them are going to work any better than the one we picked because we picked the one with the highest R-squared. There we go. Good luck with the homework.